So, sir, I think everybody's here.
Yeah.
I think everybody's here, right?
Yeah. I'm just putting on live stream, so I'm about to start.
Sure.
Oh, okay. So yeah, so we haven't got. Okay. So this I will do later. I'll start with this. Okay. So as I said in my the note that I sent you, what I'm going to introduce you today is just a very quick overview of what is a very naive version of a naive algorithm for deciding the satisfiability problem in SMT logic. Okay, it is Boolean, and it is usually used to using a Boolean satisfiability solver plus a solver to that is able to solve a conjunction of atomic formulas within the chosen theory. Okay, for example, like an LP solver can do. So let me start with a few examples. Okay, now who's there? Let me start with Ashutosh. Okay. Is this formula phi1 satisfiable, unsatisfiable, valid? Ashutosh? In the theory.
Yeah, just a second.
Sometimes I'll have to see what I did because I have some. So I'll make it smaller so that I can see it. Well,
yeah, so first one is satisfiable, I think, because x can be less than 1 and not of x equal to -1 can be like, so x can take values less
correct.
than 1.
Okay, so that is, yeah, yes. How about this? How about the second one? Some one next, Dhruvajyoti. That's because see, well, I think
So I think he is saying it in the chat. I think he's.
Okay. So yeah, good. So the last one. Let me go back here. I have to get my screen fixed because if I go into full screen mode, I can't see some part of it. Okay. How about the third one? Naveen?
Yeah, wait.
Yes, what's your answer?
Unsatisfiable.
Yeah, okay. So that's clear enough. So in each of these cases, see, there are two things, okay? One is, there's a Boolean structure, okay? That needs to be satisfied, okay? And since the atomic formulas are drawn from the theory, the constraints imposed by the theory and the non-logical symbols, etc., they'll have to be satisfied as well. So in order to decide the Boolean satisfiability or unsat and validity of those things, then you will have to determine, you will have to use Boolean satisfiability plus as well as check if the meanings of all the non-logical symbols are as constrained by the theory I present as well. So a naive solution is to construct a Boolean, I call as a Boolean over approximation of the given formula. Check first if that is sat. If that itself cannot be satisfied, then you return false. What do I mean by a Boolean over approximation? Here is what this is: theory T to B stands for theory to Boolean. Something that takes a theory, a formula, then SMT formula, and then constructs, replaces every atomic formula in that by a propositional variable. Okay. For example, for phi 1, or for this is for phi 3, I guess, okay, that I'm, okay. And actually, what I meant was there's a, yes. Such a mess I'm in. Okay. Yeah, this is for there's a typo in the thing. I meant the negation not to be there in phi 1. Okay, assume that negation is not there. In which case that is indeed. In either case, it is satisfiable, as was pointed out. Okay, so you get the Boolean over approximation by replacing every atomic formula in that SMT formula by a propositional variable. Okay, so B1 and B2 and B3. Now, this is obviously, when considered as a proposition formula, is satisfiable, right? Because you could you have thrown away the information about the actual theory atomic formula. So B1 and B2 and B3 is obviously satisfiable because it is satisfiable for two assignments, B1 and B2, or B1 and, actually more than one. So, two possible is if both B1 and B3 are true, then it is satisfiable among other satisfying assignments. So you could first use a Boolean satisfiability procedure to check when it is this Boolean abstraction is of the formula is satisfiable. Then you get the theory version of it. That is by taking the inverse of T to B, okay, by replacing the proposition variable back by the atomic formulas that they represent, okay? And then, so in which, for that particular assignment, satisfying assignment of the Boolean formula, when you put the atomic formulas back, you get x less than or equal to 1 and x equal to 1. And then you can then check this in the concerned theory. Okay, notice that every satisfying assignment of the Boolean approximation, over approximation. Why do I say it is an over approximation? Because when you replace them by Boolean variable, you're throwing away certain information. So if the Boolean structure is yeah, I mean, if the Boolean structure is not satisfiable at all, then, you know, is unsatisfiable, then you cannot have the you know, that is not satisfiable. Let's suppose it is unsatisfiable, or it will not be satisfiable at all. That's why you're returning false. So if yes, then you have to check the if that particular satisfying assignment is indeed, it preserves the theory constraints. And if it does, then you can return satisfiable, okay? And if it is not, then of course, although the over approximation is satisfiable, in the theory it is not satisfiable. Therefore, you have to look for another possible satisfying assignment of the Boolean abstraction of the original formula, and then check if that the other satisfying assignment is is satisfiable within the theory. So you could do this kind of iteratively, and you notice that when you do this, because you're checking, you know, if in the theory only a conjunction of atomic formulas, and therefore you could use, for example, you know, so when we say an LP solver for that, because that is able to handle precisely conjunction of linear inequalities. And that's how SMT solvers actually do. For example, I mean, this kind of a procedure is for various historical reasons. It's called DPLLT, because the DPLL originates what is there at the core of most Boolean solvers. Okay, so what I just now described informally here is described in this procedure. Okay, so this is what I call as a naive algorithm for solving SMT formulas, by first checking if it is satisfiable at the Boolean level by checking the Boolean abstraction, and then for each satisfying assignment, use the theory solver. Usually, we assume it works for only the conjunctive fragment of that particular theory. So, as done here, first, given a formula, it computes first as a first step the Boolean abstraction. There is a Boolean skeleton of phi, by replacing every atom in phi with a fresh Boolean variable. And then it enumerates all possible satisfying assignment of the Boolean structure. Okay, and CDCL here, it stands for a more sophisticated version of a Boolean solver, which we will see later on. Right now, let's assume that it is a black box for checking Boolean satisfiability on propositional formulas. If that itself is unsat, okay, because if there is some inconsistencies, if it has B and not B, for example, okay, then obviously that cannot be satisfiable at all, even with the theory. If the Boolean structure itself is unsatisfiable, then you return unsat. Otherwise, you then check the Then you use the theory solver to which is what a T-solve does. If it's linear integer arithmetic, in the example that I showed, you could use an LP solver. You take the satisfying assignment that is returned by the SAT solver, then you convert that back into B to T is the T to B inverse that I showed in the previous slide. And that's called a Boolean refinement of the current propositional assignment. Then you check, use the solver, the theory solver, like an LP solver, to check if it is SAT. If not, then you'll have to try another satisfying instance. And therefore, in order to get that, as you know, with like a Z3 solver, you will have to negate the current assignment, which does not satisfy the theory constraints. So then you take this formula to block the current assignment, which is not good for the theory, and then get another assignment, another satisfying assignment of the original formula. And then you keep doing this until either you get a satisfying assignment for the SMT formula that satisfies both the Boolean structure and the theory constraints, or you exhaust all possible finite assignments, possible assignments for the Boolean skeleton formula, in which case you declare unsat and get out. Okay. Yeah. So this one, as you can see, it integrates a Boolean SAT solver like the CDCL with the theory solver, both as black boxes. Okay, there are better approaches, and that's why it's called offline. There are more optimized version of this, where the two things are more closely integrated. Okay, and let's see how this thing works in the case of for a particular example. Okay. So you take this, okay, x is equal to 1, the one that was unsat, okay. So first you get the Boolean abstraction. So, one satisfying assignment is one that makes all three Boolean variables to be true, because that's obviously a satisfying assignment. Then you get what is it? Yeah, and this one, will not be. This is the other satisfying, assignment, and so on. Okay, so until this is not. Yeah, so you will have to. Okay, the step where you convert that into B to T and solve it is not exactly shown here. It's just that it shows how you can enumerate all possible satisfying assignments, and you finally get unsat. Okay, so and this is what it is. Okay, so you can have it's something like this, or there are versions in which these two things are the solvers and the SAT solving superstructure are more intimately integrated. But this is basically the basic structure. So here there are, that is what is shown in a second. So we will see a little bit more of this later in the course. But first, the point that I wanted to make was almost all SMT solvers have a Boolean satisfiability at the top level, which interacts and interfaces with a theory solver, which is a decision procedure for a conjunction of atomic formulas drawn from that particular theory. That's what it assumes. And it integrates those two things to solve the general decidability problem of an arbitrary formula in SMT logic. And how exactly these two things can be integrated more closely, we will discuss later in the course. And that's why we'll restrict ourselves when we present certain algorithms for specific theories that are of interest to us, only the decision procedure for the conjunctive fragment. There is a conjunction of atomic formulas in the theory of that is of interest to us. And that is the other point that I wanted to make. Okay, and therefore, what I will since a linear real arithmetic is of particular interest to us, since we want to apply our focus is on verifying DNNs, and therefore the first theory solver that we'll be looking at is an LP solver, an algorithm, a very popular algorithm for solving the conjunctive fragment of linear real arithmetic, and that's the simplex algorithm that we will be that I will be presenting to you today. Okay, any questions on this part? So that was a very quick top level introduction to how SMT solvers work in general, using a Boolean satisfiability solver and a theory solver which solves the decision problem for the conjunctive fragment. Any questions? Okay. Now then I will move on to as I said, okay, when we are talking about theory solvers, in this case, simplest algorithm for LP solving, we look at only the what I call as conjunctive fragment. Okay, so as you can see, of linear inequalities, both strict as well as non-strict. Okay, and that this is the syntax of the theory, the syntactic rules, and here are some examples of the kinds of formulas that we want to check the satisfiability of, okay, as a theory solver. And so with the Boolean satisfiability combination, we are able to then extend it to arbitrary SMT formulas, as I showed earlier. Okay. So simplex is one of the oldest algorithms, for numerical optimization. So here it takes an LP instance, which is a conjunction of linear constraints over real variables with rational coefficients. And also normally it's as an optimization problem, it also takes an objective function that you want to optimize, either minimize, specified over the way that is defined over the variables in the constraints. And it outputs an assignment to those variables that maximizes the objective function, while all the inequality constraints in C are solved, okay, are satisfied. Okay. Now, although simplex is worst case exponential and there are more efficient algorithms for deciding LP problem, simplex in practice outperforms most of those other procedures, and that's why it is still very popular in practice. And most SMT solvers use simplex procedure for solving in the theory of linear real arithmetic SMT formulas. Okay. Now, of course, when the requirements on simplex are slightly different for you when they are used as inside SMT solvers. So there's no objective function. We just have only the constraints. We're only interested in the satisfaction problem, given a set of linear constraints, if all of them can be satisfied simultaneously. And we need to actually be able to do it kind of incrementally, okay? I mean, this will become clear when we see more better integration of the Boolean Boolean solver with the theory solvers, okay? So there are certain kind of interface that it requires in order to be able to, in order for the theory solver to be well integrated with a SAT solver inside an SMT solver and various other things. And that is something that also the theory solvers will have to support. Okay, but for now, we will assume. I mean, what I'll be presenting is a simplex algorithm just to check satisfiability of a conjunction of linear inequalities. Okay, over here. So the first step is, that simplex algorithms do is to, there is a, pre-processing step that it, goes through, okay, wherein, so given some conjunction of linear inequalities like this over some program variables, it introduces a set of additional variables, one for each expressions, okay, term that appears in each of these atomic formula. In this case, here there are two terms, x plus y and x plus 2y minus. Excuse me? I guess that was crossed out. Sometimes these are called slack variables, so it'll transforms them into a conjunction of two sets of set of equations, okay, phi a, which equates the newly introduced variables to these terms, and phi prime, which is encodes the inequality constraints in the original formula. For example, here you will have a bunch of equalities, two new variables. I've introduced S1 and S2 to denote the value of x plus y and the other term x plus 2y minus c, and then the inequality constraints are expressed over the newly introduced variable, in this case S1 and S2. Okay. Since these are equality, this obviously, whenever this is satisfiable, this transformed conjunction of phi a and phi prime, the original is satisfiable as well, and vice versa. And that's why this is called, this step is called equisatisfying. It's not equivalent because it introduces new variables that don't exist in the original formula. Okay, so this we considered as a normal form for the LP satisfaction problem. So there are variables, these are variables that appear, the original variables, program variables, as well as the additional newly introduced variables, and you have a set of equations and a set of lower and upper bound constraints on these variables. Okay, and so the bound constraints can then be only expressed only on the newly introduced variables. Okay. Yeah, so the T satisfaction problem for linear arithmetic then consists of searching for the set of values for all the variables, both the original and the newly introduced variables, such that the conjunction, all the inequality constraints in phi prime are satisfied, and this all the equations are satisfied as well. Now, yeah, I mean, you could express them as some matrix, which has one row for every newly introduced variables, with the appropriate coefficients, which are multiplied by this column vector x, y, z, s1 and s2, which includes the newly variables. Sometimes you just keep these as equations themselves, or as equations equating the newly introduced variables to those the terms that appear. And that's what it is. Now, disequalities like t not equal to 0 can be converted by doing this, t less than 0 or t greater than 0 at the Boolean structure level. Okay, of course, this is not a conjunction, it's not in the conjunctive fragment, but you could still eliminate disequalities at the SMT formula level at this, and then you can use the Boolean satisfiability level to then reduce that into several instances of LP, several LP instances. Okay, and that's how we assume that disequalities are handled. Okay. So, any questions here? Okay. So here's a quick overview. So in this presentation, by the way, I've used the chapter 5 of the decision procedure book, and pretty much follow the exposition of simplex algorithm as described in chapter 5, as one of my footnotes earlier indicated. For your reference, you could refer to that chapter. Okay. Now, at least in this presentation, we will restrict. We will make an assumption that we do not allow strict inequalities. Okay, that they are all our constraints. The LP constraints are used less than or equal to. There's a slight extension that is required, and this algorithm that we're presenting today assumes that there are no strict inequalities. Okay, so this set of variables, the original program variables, a union of original program variables, and the newly introduced like variables, it partitions them into two disjoint sets. One set called the basic variable, and the other set called the non-basic variables. Okay. So the non-basic variable, I mean, the way they're organized is, so the non-basic variables are the algorithm, the way it operates is at every step, okay, after it performs certain major operations, it maintains this thing that the non-basic variables satisfy their constraints, okay, and the basic variables, the variables in the base, any one or more of the basic variables may not satisfy their inequality constraints. Okay, and that's how it is done. And we'll assume that equations AB equal to 0, is maintained by the simplest algorithm as what is called a tableau, with one equation that equates a basic variable as a linear combination of the linear expression over the variables in the non-basic set. Okay, so the tableau, for example, in this example that we saw earlier, okay, after the original formula is transformed into a set of equalities to the newly introduced variables and these constraints. In this case, there were no constraints on the program variables at all. If yeah, so the tableau would just have two rows, okay, which is a matrix, one for each of the newly introduced variables, S1 and S2, which equates it to the two terms in the original formula. So the left-hand side of this equation are the current set of, they are the basic variables, and the columns, one, for the terms, okay, that can be are the non-basic variables. To begin with, the newly introduced variables will be in the basic set, and the program variables will be in the non-basic set. So here the constraints are only on S1 and S2, which means the constraint on the program variables are minus infinity to plus infinity. The lower upper bounds of X, Y, and Z are minus infinity and then plus infinity. So that's the kind of, with this transformation, all the constraints are kind of transformed, are expressed on the slack, the newly introduced variables. So as the simplex procedure proceeds, variables keep moving. Okay, we'll see that they will be moved from the basic set to the non-basic set as per certain rules. Okay. So in this case, for example, so you pick one of the basic step that is performed by the simplex algorithm is to pick one of the variables in the basic set that violates its either the lower bound or the upper bound constraint. Okay. You pick one of those non-basic variables that violates its lower and upper bound constraint, and is chosen to make that variable satisfy its bound by adjusting another variable that you chosen from the non-basic, by choosing one of the non-basic set that appears in the equation that defines the basic variables. Okay, and that's and with that, and that is called the pivot operation. Okay, so the pivot operation picks up a variable in the basic set which one of either the lower bound or the upper bound is in violation. And it picks up another variable in the non-basic set, in the equation that defines that, and an update. Yeah, it also maintains, by the way, a set of assignments to the variables, and it adjusts the current assignment to reflect the adjustment made. Okay, so what it does is it either it changes the value of the non-basic variable chosen by either increasing it or decreasing it to make the variable, the basic variable that is chosen to make it meet, satisfy its constraint. Okay. So, and then it changes, performs only the minimal adjustment required for xj. For xi, it changes xj minimally in order to bring xi to reach its bound. Either if the lower bound is the constraint is what is being violated, then it changes the value of the non-basic variables to make xi meet its bound constraint by either increasing or decreasing it to so that it will be exactly equal to its bound. And then it also, and then it flips that variable. I mean, that's why it's called pivot. Okay, after it does the adjustment, the variable, the non-basic variable whose value is adjusted might no longer satisfy its bounds, and therefore it also flips those two variables by moving the basic variable whose value got to non-basic variable to the n set, and moving the non-basic variable whose value got adjusted to make xi meet its constraint into the b b set, because the non-basic variable whose value got adjusted may not may no longer satisfy its constraint. Okay, and then since now the b and the n set have changed, so what it does is it also changes the tableau to the equations in the tableau to reflect the new set of basic and non-basic variables. For example, so here, so if the original tableau was this one, say, and the this is in the beginning, and say your starting assignment, variable assignment was this one, all variables being assigned to 0. And with this assignment, you can see that the constraint on S1, I'm sorry, S2 is violated. S1 is still true, because S1 requires that it be less than or equal to 2. So S1's constraint is satisfied by this initial assignment, but S2's constraint is violated. Okay, and therefore it has to now it picks S2 in the basic variable S2 to increase its value to 4 by choosing, I mean, it could either have chosen X or Y. It chooses X to adjust its value in the current assignment by increasing it to 4 to make S1, I'm sorry, S2 reach its upper bound. I mean, lower bound. Sorry. Okay, it's lower bound. As I said, it always changes, adjusts the value of the non-basic variable in such a way that the basic variable meets its bound constraint by actually making it become equal to one of its bounds. And then it now has to, so the S2 will have to be moved to, the non-basic set. And X, which was previously in the non-basic set, will get moved to the basic set, and that is part of the pivot operation. And in order to get that movement reflected, we redefine. So X, the X, the new variable, by moving the variables around in this equation, so that every variable in the basic set is preserves the equality. Okay, so that's how so variables are moved around such that each of the basic variable is defined in terms of the new set of non-basic variables, which in this case includes S2. So once that is done, you have to, the pivot operation also updates, okay, the assignment, the current assignment to variables as per these equations. So it updates the basic variable, the pivot that got pivoted, the basic variable that got pivoted into this pivot operation to its lower bound or upper bound to which it is set. In this case, so S2 is set to 4, and X is whatever adjustment that was needed. Okay, and that you can actually, after you get these equations, you can plug in that value, and you will notice that the non-basic variables that were left alone in N, their values will not get updated. Okay, so the basic variable that got moved, its value is updated to to either the lower bound or upper bound that got that it was violating, and the non-basic variable, and so. But then after that, all the basic variables in the basic set will have to be updated as per the new values for the new non-basic set. Okay, so that is the thing, and then that's how it does. Okay, so it repeatedly performs this pivot operation until it is satisfiable. I mean, as long as if it at any point, if it cannot find any variables in the non-basic set, to adjust its values such that the basic variable, which is violating the constraint, violating the constraint, cannot be fixed, then you declare it is unsat. Okay, and that's how it does. And there is another thing. So there is an ordering. Okay, it also, since multiple at any particular step, when you do the pivot operation, there's a choice. You can have multiple variables that can be used. In this case, for example, you could either have used chosen X from or Y in order X, Y, or Z in order to adjust their value from the non-basic set, such that S2 was set to its lower bound. Okay, so, and if there are multiple choices available for to pick from the non-basic set, and there could be multiple choices. In this case, only S2 was violating the basic variable S2 was violating, but you could also have multiple variables in the basic set. Then there'll be you need to choose. In either case, the algorithm uses a fixed ordering on the variables, and if there are multiple choices available for you to choose either the basic variable or non-basic variables to pivot, then it uses the smallest among them. Okay, in that order, and this we will see later is required to guarantee termination of the algorithm. Okay, so let me illustrate this. Okay. Okay. So with that kind of informal introduction, let me get to. So the state maintained by the simplex procedure. So there is a tableau which keeps changing after each pivot operation, and it is maintained, as I said, as an equation equating each of the current basic variables to an expression in terms of the current non-basic variable. Okay, it's a linear combination. And then there are the current basic variables indicated as the rows of tau, and the current non-basic set of variables. Okay, and then another component of the state that simplex procedure maintains is a variable assignment. Okay, to all the variables in N as well as B, which gets updated as well. Now there is a fixed set of lower and upper bounds for every variable, in B union N, and a fixed strict order on the variables V to consider them, to choose which two variables from the basic and one variable from the basic set and the non-basic set to pivot. Okay, these two things, the last two bullets, they don't change; they are fixed for the entire duration. So the initial state of the in the initial state, we assume that all the variables are assigned a 0. Okay. In the yeah. Okay, so here is the algorithm. Kind of in pseudocode for the algorithm, as I said. So if all the constraints are okay, you keep doing it until select. Yeah. So first you see if any of the basic variables in the any variable in the basic set violates either its lower bound or its upper bound. If there's no such variable, remember that every variable in the non-basic set satisfies its to begin with. It always satisfies its bounds. Okay, so you only need to check if there are any variables in the basic set if it violates. Okay. If there's no such variable, then you know that all the variables in N union B meet satisfy their constraints, and therefore you can return satisfiable. If there is one or more variable, then you pick the smaller that violates either its lower bound or upper bound constraint. Then you pick the smallest in the variable ordering, that variable, and select the smallest non-basic variables. For example, if the non-basic variable chosen violates its lower bound, it's less than its lower bound, then you will have to select the smallest among the non-basic variables in the set N, such that it has the required slack to adjust its value such that xi, value of xi, can be increased to Li. Okay, and this can be done in two ways: by looking at the coefficient in the of the chosen non-basic variable in the equation defining xi. If that coefficient is positive, then of course the value of xj, the non-basic variable chosen to adjust its value, has to be reduced, and you will do that only if it is there is slack. Okay, if that itself is within its if it's less than uj, then you can reduce it. Okay, or if the coefficient is negative, then you have to ensure that xj is greater so that it can be increased. Okay, so that if you so xj has to be greater than its lower bound, the non-basic variable, so that its value can be decreased to increase the value of xi. Okay, so this is one. So you have to check if the non-basic variable has enough slack either at the high end or low end in order to allow for the value of xi to be adjusted to its lower bound, and that's what that check is done. Okay, if there's no such xj, then it returns unsatisfiable. Okay, but if there is one, then it does the pivot and update operation that I informally explained in the last slide. Similarly, there is the other case when the violation is because the upper bound is being violated by the chosen basic variable. then you select the, once again, select the smallest xj such that the dual of this, okay? So in this case, since it is violating the upper bound, you will have to decrease it, and that's what it does. So if it is the coefficient is negative, coefficient of the chosen non-basic variable in the equation in the tableau corresponding to xi is negative, then you will have to decrease it such that so you have to increase it, okay, and therefore you have to ensure that the xj variable has enough slack, okay, that it is less than uj, or if it is greater, then it has to you have to ensure that its lower bound, it is greater than lower bound, so that it can be decreased such that the value of xi can be decreased. And after that, it does the pivot operation. If there's no such, once again, you return unsatisfiable. Okay, and that's So yes, so it keeps doing this until it either finds all the constraints on the variables are satisfied, or if it hits a point where you cannot do any adjustment. You cannot. It is not possible to pick any variable among in the non-basic variable to do the adjustment. Okay. Yeah, this is a formal description of what I just have said. Pivot and update. It takes a variable in the basic set and a chosen variable in the non-basic set, a basic variable in the set that is violating one of its constraints, and a variable in the non-basic set which can be used to adjust its value to make xi satisfy its constraint. And this v is either the lower bound or the upper bound, okay, to which xi has to be adjusted. And then it does, it flips the variable, modifies t to redefine all the equations, and then it modifies beta by updating the basic variable that is whose violation is being fixed to either the lower bound or the upper bound as per the violation. And after that, it computes all the it updates all the values of the other basic variables which remain in the basic set after the pivot operations. And that's what this formal description of what pivot and update does. Okay, so let's look at how on this example, okay, to illustrate the procedure. Okay. Okay, so here is the set of equations. Okay, so the equations, the original equations are these things: 2x minus y greater than or equal to 0, minus x plus 2y is greater than or equal to 1, and x plus y is greater than or equal to 2. And that is now transformed into a tableau with one new variable, additional variable introduced for x plus y, and these terms that appear here. Okay. So by the way, I mean, I skipped this this slide. Sometimes it is useful to view this LP problem in the constraint solving problem in the LP problem as in the Euclidean space. Okay, each equality, I mean, because phi, so what it has is a bunch of equalities after the transformation, and the bound constraints on all the variables. Okay, each equality defines a hyperplane. Okay, for example, a line in the two variable space. Okay, each equality here, for example, S1, S2, S3, they correspond to these lines S1, S2, and S3 shown here. And each inequality constraints defines what is usually defined as a half space. Okay, that is a plane in a two-variable space. So for example, x plus y greater than or equal to 2 is the region above the line S1. Similarly, the constraint, the inequality done by 2x minus y greater than or equal to 0 gives the region below the line S2. And similarly, the other constraint, the third constraint is the thing. So a solution then is an intersection of these three hyperplanes or planes in 2 dimension. And that is what is usually called the convex polytope. Okay, these are in 3 dimension. They form polyhedrons, and in 2 dimension they are planes. And the half space, that is the plane in the case of in the 2-dimensional space, that is defined by the intersection of all these hyperplanes. The planes is the region, the solution space for the variables. Okay, and there are the points here. The extreme points are the ones where some subset of the variables take assume their lower or upper bound. So, for example, you can have this C could be a possible solution, or this one. So actually anything in this area is a solution. Okay, so let's see how this simplex procedure does that. Okay, for this example, unfortunately I can't see the whole space, therefore I'll reduce it a little bit so that I can see. I hope this is big enough for you.
I think it should be okay, sir.
Okay. Okay. So I'm assuming that this is the variable ordering that is used. Okay, x, y, s1, s2, s3, and these are the bound constraints on s1 and s2. There's no constraint on x, y, or z. So this is the initial tableau, in which the basic variables are just the additional variables that are introduced, the newly introduced, and they are equated to the terms. And the assignment beta, as I said, it always, the initial assignment is all 0. Okay, this corresponds to the point A in this picture, and obviously that is outside the space, solution space, and therefore it violates. Okay, which ones? Both S1 and S3 constraints. The constraints of S1 and S3 are violated. Okay, S2 is preserves its constraints. So we have a choice of either picking S1. I'm sorry, either picking S1 from the basic set to as the variable to make. To get its constraints satisfied, or S3. Since S1 is lower in the variable ordering that we have chosen, we pick S1, and S1 is defined to be x plus y. So once again, we have a choice of x and y, but x appears before y, and therefore the non-basic variable to adjust its value is chosen to be x. Then you determine, so you have to increase S1 to 2 since it's 0 to make S1 satisfy its lower bound. And so you see how what the slack value, how much x has to be increased. In this case, it is 2 by using that equation, okay, to compute the value of how much x has to be increased by, which in this case is 2. So, and then, so after that, what you do is you flip the variables x and s1 by moving s1 to the non-basic set, and x from the non-basic set to the basic set. As a result of which, we'll have to adjust the tableau, and the tableau is updated as shown here. So by defining x in terms of s1 and y, and then plugging x inside s2 and s3, so that s2 and s3 are now defined purely in terms of the non-basic variables, the current non-basic variables, and you update the assignment to variables by updating x, the two variables that got pivoted. Okay, x was set to its lower bound, and I'm sorry, not s1 was set to was made to increase to 2 by setting s1 to 2, and then x is now set to whatever value that it got adjusted by. Okay, since it was 0, it is increased to 2, and that's how. And all the rest, all the other non-basic variables like y and z, which remained in z, will retain their assigned values, but the other basic variables which were retained in B will have to, their value will have to be computed, since the value of x has been, value of s1 has been changed, and that's how you compute the new assignment. So what then happens as a result of this is your current assignment moves from point A to point B, which is still outside the solution space, because S3 is still, even with this new assignment, S3 is still violates, okay? Since there is no constraint on X, the basic, X is not in violation, but S3 is in violation. S2 is, within its constraint, because it's, 4 times minus 3, and S2 has to be greater than or equal to 0, and it is 1. I'm sorry, S2 is 4, I guess. Yeah, 4 minus 0, yes. So that is not in violation, and therefore you then, so the only choice for the variable to be fixed is S3, and you still have a choice of either S1 or Y to adjust. Say we pick Y, and then you do the same operation, and that moves the, updates the current assignment such that B gets moved to C. And since C is in the solution space, so after that, all the pivot operation, Y gets moved to the basic set, and all of them will be, there's no more violation on any of the basic variables, and so therefore the procedure stops. Okay, and see that, so if you go to this is one I discussed. So if you use a different variable ordering, here's I have illustrated, and you can follow that at your leisure. So if I change the variable ordering to this one by rearranging the S3, S1, and S2, and you will see that you get another possible solution. So from A, you move to a point D, which is the intersection of S3 with the x-axis in the negative quadrant, and then it gets moved to C. Okay, so from here A to this point D, and then to C. So yeah, so different depending upon the ordering, some dictates how which one you will get, and which solution you end up getting, and that's how it explores. Okay. Any questions on how the algorithm works? Yeah, I would suggest that you actually try a different variable ordering. So there must be a way, a sequence of pivot operations that gets you to this point here, another possible solution. So by moving A up to this point and then getting back to that, and see if you could use a different variable ordering that will get the simplex procedure to get to another possible solution that is corresponds to the intersection of at this point here that I'm showing the cursor at. Okay, so what I will some important questions, okay, regarding the correctness, okay, which we will get to in the next class. One is these two questions are relevant for any decision procedures, okay, satisfiability decision procedures, even at the Boolean level or at the SMT level. One is soundness, and this is concerned with the question if the answer produced by the decision procedure, simplex in this case, is correct, okay, that it is sound whenever it terminates, okay, that it is correct, okay, that indeed when it says yes, it is satisfiable, it means the input set of constraints, it means that the variable assignment that is produced at the end is indeed a satisfying assignment for the set of input constraints, okay, and if it says no, that it means that the set of input constraints is unsatisfiable, that there is no satisfying assignments. Okay, that is one important question that one has to always address one has to answer in analyzing the correctness of any decision procedure. The other an important property of a decision procedure is completeness, which addresses this question, answers this question. Does the procedure produce an answer for every possible input situations? Okay, in this case, does it produce an answer conclusively for every possible finite set of inequalities over linear real arithmetic? This question itself, since we are talking about algorithms, consists of showing that the algorithm always terminates, because if it does not terminate for some input situations, then of course you cannot have a conclusive answer. Therefore, it requires you to show that the algorithm always terminates, and it produces, when it terminates, a conclusive answer of yes or no. Okay, these are the two important questions. Okay, so yeah, and we will look at this next time. Okay, and briefly, doing showing this formally would be quite instructive, but I will describe, try to convince you through a semi-formal argument as to why simplest procedure indeed terminates for all cases, always terminates, and when it terminates, if it produces a SAT, that indeed is a valid, is a legal satisfying assignment, and when it says no, it means that there is no satisfying assignment. Okay, and the termination argument Yeah, I mean, the soundness argument is, maybe I'll get to it next time because maybe, yeah. So the procedure maintains certain invariance after every pivot operation, okay? That, that is always satisfied after every operation, and that is used to show its soundness. Now, the termination argument relies on the fact that the possible states, because there are only finitely many equations, equations and inequalities, and there are only finite fixed set of L and U, that it uses the argument that will mean that the number of states that the set of states that the procedure will have to explore is always configurations, okay, or states that it has to explore is always finite, okay? And the strict ordering on the variables ensures that there is no loop in the sequence of configurations that the simplex procedure explores, and it, whenever there is a solution, that it indeed gets to a satisfying solution. So the termination argument is based on the fact that there are no loops in that in the sequence of configurations that simplex procedure explores. Okay, so yeah, I think I'll stop here and take any questions you may have. Okay, if you don't, please, as I suggested, please try a few more examples. I mean, you can use the same example in this slide with a different variable ordering to get a different solution, so that you will understand the nitty-gritties of the detail, of the algorithm. And I will, in the next class, cover a little bit about why this algorithm is sound and always terminates. Okay, when it terminates, it produces a sound result. Okay, you give some intuition as to why that is the case. Okay, let's stop sharing.